I need to get I. Since it's a disk, okay? If I go back to my table for moments of inertia for something that is a disk, then what I'm going to get is 1/2 mr squared. So I is equal 1/2 mr squared. So in this case, it's 1/2 times the mass, 0.500 kilograms, times 0.25 meters squared. So I'm going to plug things in down here. So I have T1 times 0.250 meters. And why did I put 3 there? That should be T4, magnitude of T4, which is T2 times 0.250 meters has to equal 1/2 times 0.500 kilograms times 0.25 meters squared, and alpha is equal to A over 0.25 meters. And alpha should have been negative, so I'm going to put a negative sign there. Okay? Now, notice the 0.25, the 0.25, and one of those 0.25s divide out there, and then the other one divides out there. So I've got T1 minus T2 equals 0.250 kilograms A. Okay, guys, let me see if you can see. Just barely, but we can see it. So now I have this equation for my pulley, and then I have T1 minus 9.80 newtons is equal to 1 kilogram A, and I have T2 minus 29.4 newtons equals minus 3 kilograms A. I have 3 equations and 3 unknowns. Now, notice I've got a minus 2t here, I've got a plus 2t here. If I were to multiply this by a minus 1 and then add all these together, the minus 1s divide out, the T1s add out, the T2s add out, and I have 9.80 newtons minus 29.4 newtons is going to equal, let's see, a minus 3, a minus 1, so that's minus 4. 4, and then I get a minus 3.75 kilograms A. So 9.8 minus 29.4 gives me a minus 19.6 newtons equals minus 3.75 kilograms A. Notice the negative and the negative divide out, and I get A, the acceleration, to be 5.23 meters per second. Now guys, another way you could have done this is you could have solved this for T1 and this for T2 and plugged them in up here and then solve for A. So there's more than 2 ways to solve that system of equations. Okay? But you ought to be able to do a problem like that. All right. Now, let me look at problem 86 and see if we really need to do that right now, or if we can move on. 86 is very similar to the problem I just did. You guys can try that one on your own. Now, when we start talking about rigid bodies, we can get into static equilibrium. Okay? When an object is in static equilibrium, remember that it's sitting still. If it is sitting still, has no translational motion, it has no rotational motion. So the sum of the forces has to be 0, and the sum of the torques have to be 0 for any point on the object. So you can choose any point on the object and make it a pivot point and look at the sum of torques about it. Okay? But the sum of the torques have to be 0. So when we look at an object that's supposed to be in static equilibrium, we can determine what the forces on the object have to be by either looking at the sum of the forces or the sum of the torques or a combination. If you're going to take statics, you're going to do a lot of this. So we're going to look at problem, let's see. We're going to look at problem, first we're going to look at problem 32 at the end of the book, at the end of the chapter, and then we're going to look at problem 59. Okay? So there are two good problems for us to look at. Talk about static equilibrium. Okay. Problem 32. It says a 5 kilogram cat and a 2 kilogram bowl of tuna are at opposite ends of a 4 meter long seesaw. How far to the left of the pivot must the 4 kilogram cat stand to keep the seesaw in balance? Okay? So look at that problem. We always start a problem with a picture. And for a rigid body, we always draw the body that's going to be rotating, and then we show all the forces and the pivot point. So here we go. Okay, pivot points here in the middle. And I've got a force here. I'll call it force 1. I've got a force down here. Force 2, and then at some distance d from the pivot point, I've got a force 3. Now the magnitude of force 1 is going to be the mass of that cat times gravity, and that is a 5 kilogram cat, so 5 times 9.8. Force 1 is 49 newtons. Force 2 is that tuna bowl, and it's 2 kilograms, so 2 times 9.8, that's 19.6 newtons. Force 3, that is a 4 kilogram cat, 4 times 9.8, 39.2 newtons. Okay? This distance is 2 meters. And this distance is 2 meters. Now, the pivot point here has a force F4 on it because the pivot point is pushing up. If we look at the sum of the forces in the y direction, we would have 2 unknown forces. That's not going to do us a whole lot of good. So what we want to do is we want to look at the sum of the torques about the pivot point. And that should be 0. Okay? So if I start looking at this, then I've got a torque 1, which is going to have a magnitude of 49 newtons times 2 meters. And anytime you've got a 90-degree angle here, the sine of 90 is 1. I'm calculating this as a magnitude, so that's 49 times 2. That's 98 Newton meters. The magnitude of torque 2 is going to be 19.6 newtons times 2 meters times 1. So 2 times 19.6, that's 39.2 Newton meters. And of course, force torque 3 is going to be 39.2 newtons times D times 1. Okay? So my force 1 is going to want to rotate it clockwise. So torque 1, vector-wise, is a minus 98 newtons. Using the same logic, torque 2 is going to be a plus 39.2 newtons, and torque 3 is going to be a plus, excuse me, this should be, yeah, plus 39.2 newtons times D. So if I look at the sum of the torques, I get a minus 98 newtons plus a plus 39.2 newtons plus 39.2 newtons times D equals 0. So 98 negative plus 39.2, I have a minus 58.8 newtons plus 39.2, well, those are Newton meters, newtons times D equals 0. So I get D to might be a 1.5 meter location. So he's out there quite a distance. Okay? Not too bad, right? So let's look at another problem. We're going to look at problem 59. It says an 80-kilogram construction worker sits down two meters from the end of a 1,450 kilogram steel beam to eat his lunch. What is the tension in the cable? Okay, guys, let's draw a picture and look at all of the forces. Okay? Our object that we're interested in, whether or not it's going to rotate, is that beam. Okay? It's got a tension T here. It is a 6 meter long beam, so 3 meters in, I'm going to have the force due to gravity acting on the beam. Okay, the wall is going to push out a force X here. The wall should pull up force Y here. And there is force from the man. Okay, and he is 4 meters out. Okay, now force due to gravity here is going to have a magnitude of 450 times 9.8. So that's 1.42 times 10 to the 4 newtons. The force from the man is equal to the force due to gravity acting on the man, and he was 80 kilograms times 9.8. So that's 784 newtons. Okay, and that's all we know. Now, we are asked T, the tension. So this is one of those cases where I need to choose my pivot point carefully. Notice that in this diagram, we have 3 unknown forces. The tension, force X from the wall, force Y from the wall. But tension is what I want to know. So the best thing to do is pick my pivot point here, because we know any forces acting through the pivot point will not cause a rotation about that pivot point. So by choosing our pivot point there, we have eliminated those forces when we've got to look at sum of torques. So I'm going to look at sum of the torques about the pivot point, PP. Okay? All right. So torque due to gravity is going to have a magnitude of 1.42 times 10 to the 4 newtons times 3 meters. And again, it's a 90-degree angle. So I know the sine of 90 is 1. So 3 times 1.42, I get 4.26 times 10 to the 4 Newton meters. The torque from the man is going to be 784 newtons times 4 meters. So that's 3.14 times 10 to the 3 Newton meters. Now, the torque from the cable is going to be T times 6 meters. Now, the angle here was given to us as 30 degrees. Okay, so I have the sine of 30 degrees. 30 sine times 6 gives me 3. So I have the magnitude of T, 3 meters. Now let's look at the sum of the torques. I have torque from force due to gravity, and that's going to cause a clockwise rotation. So I have a minus 4.26 times 10 to the 4 Newton meters. From the man, it's also going to cause a clockwise torque, so that's going to be minus 3.14 times 10 to the 3 Newton meters. The cable is going to cause a counterclockwise, so it's going to be plus the magnitude of T, 3 meters, all having to add up to be 0. So 4.26 EXP4 plus 3.14 EXP3. Divide that by 3. If I solve for T, I get 1.52 times 10 to the 4 newtons. And that's the magnitude of T. So you should be able to do a problem like that. Okay? Not bad. All right. I'm going to stop right here for a second because my battery is getting very... Now, when we're looking at torque and we're looking at rigid bodies and we're looking at rotational motion, one of the things that we can talk about is the stability of a car or a truck or an SUV. And the stability, okay, has to do with whether or not the car will roll over. Cars and trucks have a stability factor, okay, based on the center of mass of the object and how high the center of the mass of the object is relative to the ground compared to wheelbase. Okay? The critical angle is the inverse tangent of T over 2h, where T is the distance from wheel to wheel, or the wheelbase, or sometimes called the track width, and h is the distance up from the ground to the center of mass. For your average car, the critical angle is 57 degrees. That's the maximum angle the car can tilt from the ground before it rolls over. Sorry guys, the screen just decided to go out on me. And being a butt. Okay? For an SUV, the critical angle is usually about 47 degrees. And that's because they sit higher above the ground. Okay, more ground clearance. So if you think about this, okay, if here is the center of mass, as long as it stays on this side of the pivot point, it's going to want to pull the car back down onto its wheels. As soon as the center of gravity gets on this side of the pivot point, the car is going to flip. Okay? So if you see somebody riding, you know, in one of those stunt shows on two wheels on one side, they're doing a very fine balancing act. To drive any distance up on an edge like this, you're going to have the center of gravity over the tires. Perfectly over the tires. So, if you want a car or an SUV or anything to be as stable as possible, you want a critical angle below 50 degrees. And that means if you want it higher, you would need to widen your tire base. Okay? Just kind of a piece of information. Now, let's think about objects that roll, like a ball or a wheel or a hoop. Rolling motion is a combination motion. The object is rotating as it is moving forward. So it has translational motion and rotational motion. The velocity of the center of mass of my rolling object actually equals the tangential velocity of the rolling object, which equals r, the radius of the object, times omega, its angular speed. So a rolling object has translational kinetic energy and it has rotational kinetic energy. Okay? So the kinetic energy for a rolling object equals 1/2 I, the center of mass, omega squared, plus 1/2 mv, the center of mass squared. Now, we know that the velocity of the center of mass can be thought of as omega squared r. So it turns out that the kinetic energy is 1/2 I center of mass plus 1/2 mr squared times omega squared. So guys, one of the things that this tells us is when we're rolling objects, the moment of inertia of the object is going to affect the kinetic energy of the object and the angular speed of the object, so that they're going to have different speeds at which they roll down an inclined plane. Because when you're rolling down an inclined plane, remember you're taking gravitational potential energy initially, if you start it from rest, and turn that into kinetic energy final, okay? So that we can see that the kinetic energy final has to equal mgh. You have different angular moments of inertia, then you're going to end up with different angular speeds. Okay? Now, if you look in your book on page, let's see, what's the page? If you look at your book on page 317, figure 12.43 talks about if you'd had a particle, you had a solid sphere, you had a solid cylinder, and a circular hoop, okay, all of the same mass, then who would reach the bottom of an inclined plane first? Okay, so figure 12.42 on 316 and figure 12.43 on 317 would be worth a look for you. Now it's time to talk vectors. Okay? And we're going to talk about vectors and torque. I've been hinting at and pretty much outright saying that torque is a vector. Now we get to talk about what direction that vector points. Up until now, we've talked about counterclockwise being positive and clockwise being negative, but the question is, why is counterclockwise positive and why is clockwise negative? Because we know the magnitude of the torque is equal to Fr sine phi, but where phi is the closest angle between the, the radial line and the force. But why? Why is counterclockwise positive? Why is clockwise negative? Well, it turns out that when we're looking at calculating torque, what we're really doing is we are doing a combination of two vectors, the F vector and the R vector, and what we're doing is a cross product of two vectors. Now let me draw a picture. Okay? So, if this is my object, there's my pivot point, and let's say I'm applying a force F here. Okay? If this is a vector pointing from the pivot point to the point of action, there's my force. R, my extender, is here. There's my angle phi. Okay? We are doing a cross product. The torque here is equal to vector R cross vector F, which equals R, the magnitude of R, times the magnitude of F, times the sine of angle phi, which is the angle from R to F. Okay? In this case, it would be an angle less than 90 degrees. if I had a pivot point here, and I had a force F here, and my extender line here, R. Okay? That would be our angle phi. Phi here is greater than 90 degrees. Actually, phi should be measured this way. R cross F. Cross product of two vectors. So, all right. Using vectors in component forms. If we were doing a cross product of vectors, A cross B, A and B are in the XY plane. The resultant vector C is a vector that points along the Z axis, okay? The magnitude of vector C is AX times BY minus AY times BX. If I have the vector A being AXI, AYJ, BXI, BYJ. So when we do a cross product, okay, and you've been doing this in calculus and other classes, A cross B, okay, AX BY minus AY BX K. So the cross products of two vectors gives us a new vector that is perpendicular to the plane formed by the first two vectors, which would be along the Z-axis. Okay? I also want you to remember that cross products are not commutative. A cross B does not equal B cross A. They're going to have the same magnitude, but they're actually going to point in the opposite direction. Okay? Now, I want to talk right-hand rule here for a second. And then we're going to do a couple of examples. In the right-hand rule, you're going to take your right hand, okay, and your thumb is going to point in the direction of the first vector. Your pointer finger is going to point in the direction of the second vector, and then you fold your other fingers up to show you the direction of the cross product vector. So if I do R cross F here, this vector is going to come out of the board. Okay? R cross F. If I do R cross F here, I get something going into the board. RF into the board. Okay? Okay. So think about your right hand rule. If the force is going, if the torque is going into the board, like we see up here. Let's see. Excuse me. Forces RF out of the board. If the force is coming out of the board, you're looking at a counterclockwise rotation. You got a positive Z axis. Positive Z is coming out of the board. Here, R and F, I'm going into the board, I have a minus Z axis. So R, F, out of the board, R, F, into the board. Positive Z-axis torque, negative Z-axis torque. Okay, so we're going to look at problem 37 at the end of the chapter and just do a torque calculation. Okay? Now, if I look at 37A, says find the torque, and we are given a vector B that has a magnitude of 4 units and a vector A that has a magnitude of 6 units, and we're given a 45-degree angle there. Okay? But this is the point where they connect, so I really need to think about A as being over here. So if that's 45, then this angle from A to B is 135 degrees. So our cross product, A cross B, would be 4 times 6 times the sine of 135. So 4 times 6 times 135 sine, and I get a 16.97, so 17 as the cross product. Okay, if we look at B, this was A, I've got a vector going this way and a vector going this way. This one's 6 and this one's 4. This is vector C and this is vector D. Okay, the angle in between them is 180. So if I go C cross D, I have 6 times 4 times the sine of 180 180, if you take the sine of that, you get 0, so the cross product here is 0. Okay? So, cross products. You should be able to do a cross product. Now, I am going to also do a vector, well, no, that's all I want to do. Okay? So, your torque's either going to point along the plus z-axis or the minus z-axis. We always talk about the torque pointing along the axis of rotation, or the axis about which something is rotating. All right, now, angular momentum. Okay, momentum, remember we talked about earlier, linear momentum or translational momentum is the mass times the velocity. P, the momentum, is m times v. Momentum is a vector quantity, and momentum is related to both mass and velocity. Remember, it's how Newton really worked out things initially, and we've modified it with time. Well, guess what? There's a rotational equivalent. Okay? Angular momentum, L. L is equal to I omega. Or you could say L is equal to R times P, the moment of inertia. Not the moment of inertia. L is equal to R times P, the momentum of an individual part. or MRV sine beta. Now don't worry about that too much, but know that L is equal to I omega. And we use the right hand rule. Okay? If an object is, if you are using the right hand rule in another way, okay? If you wrap your fingers of your right hand in the direction of the angular velocity, your thumb's going to point in the direction of the angular momentum. Okay? So, but if it's spinning counterclockwise, the angular momentum points this direction. If it's rotating clockwise, okay, points in the opposite. Essentially, well, yeah, the way it's rotating, L is going to point in the same direction as omega. So L equals I omega. Roll this up a little bit. So let's look at problem 45. Let's see. Well, no, it said 44. Problem 44. 44. Let's look at it. All right. Should go this way and go down. It says, what is the angular momentum vector of a 500-gram rotating bar shown in figure 12.44? So we're asked the angular momentum. Okay, and we're told that the mass is 500 grams. And looking at it, the length is 2 meters, and the pivot point is at 1 meter. Now it's a regularly shaped object. So if we go back and we look at our table for moments of inertia. The moment of inertia, I, is equal to 1/12 ml squared when the pivot point is in the middle. Okay, so this is kind of our setup. 500 grams, that's 0.500 kilograms. So the moment of inertia here is 1/12 times 0.500 kilograms times 2 meters squared. So 0.5 times 2 squared divided by 12 is 0.167 kilograms times meters squared. And I know that L, the moment of inertia, is equal to I times omega. And the problem tells us that it's rotating at 120 revolutions per minute. So I need omega is 120 revolutions per minute. It's not in SI units. 2 pi radians for every 1 revolution, 1 minute for every 60 seconds, 120 times 2 times pi divided by 60 gives me 12.6 radians per second. Now, looking at the image, okay, this thing is rotating counterclockwise. So omega here is positive. So I would have 0.167 kilograms meters squared times 12.6 radians per second, and that's positive. So I get 2.098, so 2.10, and I have kilograms meters squared over seconds as my units. Okay, and it would be positive because it was rotating in the counterclockwise direction. Now, the last thing I have to bring up is the fact that if an object is not interacting with other objects, okay, we can see a conservation of momentum. So L initial has to equal L final. So I can say I initial omega initial has to equal I final omega final. Kind of like when we talked about collisions and explosions, the momentum initial has to equal the momentum final. Well, if this is not being acted on by an outside object or an outside force, everything's inside the system, the angular momentum to begin with has to equal the angular momentum final. Okay, you say, where would this happen? Well, if you think about a skater, okay, they are spinning and their arms are out and they bring their arms in, they've changed the shape of their body, which changes their moment of inertia. If you change the moment of inertia, then to maintain the angular momentum, you have to change the angular speed. Moment of inertia is greater when the object is spread out. When it gets smaller, like drawing the arms in, the moment of inertia decreases. So when the arms are pulled in, they're going to spin faster. When they throw their arms back out, they spin slower. Okay? So that's conservation of angular momentum. And it's this very simple equation. Okay? The other place where this would pop up is, let's say, when you're riding a bike. When you're riding a bike and you get the wheel spinning, it's much harder to fall over. Think about trying to sit on that bike if the bike isn't moving. You topple over fairly easily. But once you get the wheels rolling, you don't. And that's because you've got angular momentum. Okay? And the angular momentum wants to be conserved. You have to apply forces on it to change the direction that that angular momentum vector points. So it takes quite a bit more force to knock you over when you're rolling than when you're not. In lab, I'll let you play with a bicycle wheel and experience conservation of angular momentum. All right, guys, perfect place to end. Now, if you look at the end of the notes, there are a list of questions that it would be helpful for you to work at the end of this chapter. I would suggest you look at them. On to the next chapter. We skipped chapter 13. The next chapter is chapter 14.